Hello guys, and welcome to this kind of sort of tutorial. It's actually an explanation on my Wolfram cellular automata implementation. So I have to say that this implementation is based on the Daniel Shiffman's implementation on his Nature of Code book. And yes, he made it for processing, and I adapted it to Max. Obviously, I had to change something, but the functioning and yes, the algorithm is almost the same. So you can see a YouTube video of Daniel Shiffman explaining his Wolfram cellular automata, and I recommend if you're interested to watch his video. But anyway, now I'm going to give you a little introduction on the subject. Let's see. Let's first let's see what we are talking about. This is my implementation. It's a cellular automata, the most simple cellular automata you can have. And in my implementation, it goes from bottom to top, like in an infinite visualization. So yes, you have 256 rules, and some rules are more interesting than others. For example, number 225 is one of my favorite. You can also change the size of the system. So you get the Wolfram cellular automata going on from bottom to top, and yeah, it's quite cool. I implemented this grid, which is good, especially for smaller cases. Yeah, that's it. So let's see what we are talking about. We have a one-dimensional cellular automata. One dimension is just one row, like this one, but visualized in a two-dimensional grid. We are just putting every row above the other, in a way below the others actually, so we can have this two-dimensional visualization. So how does it work? We have the first generation, and we have the generation below are based on the outcome of the previous cells, based on a neighborhood of 3 cells, which is the simplest neighborhood we can have. So for example, these 3 cells are a neighborhood, and the outcome of the middle cell is based on the three cells which forms a neighborhood. So we have actually 8 possible neighborhood configurations with three cells. You can see this one, and so we can actually establish an outcome for every possible configuration, which is what I did here. Like I did this arbitrarily. I decided that if we have 3 zeros, we get a 1. If we have a 0, 0, 1, we get a 0, and so on. And so the rule defines the outcome for every possible neighborhood. So these 8 numbers are called a rule. And it's actually, since we have 8 numbers that are 1 or zeros, this is actually a byte. So we have 2 at the 8 possible rules, 256 possible rules, which is the size of a byte in bits. And so, yes, every rule is actually defined by a char number translated into bits. So, for example, if we want the rule 90, this is actually the bit representation of the number 19. The binary representation of the number 90. So, for example, this is an integer, and let's say that this visualizes binary. So let's pick a number, 90. Okay, so this lacks a 0 in the beginning because we always want to have 8 numbers. These are actually 7, but this is basically a rule. If we have a 0 before this first one, we have a rule. So every number is actually a rule. This is the possible outcome for all possible neighborhood configurations. Okay, so I hope this was clear, even if I don't think so. But you can get better explanation on the Daniel Shiffman videos. So let's move to the Max implementation. So first of all, we have to fill all the possible 256 rules. And let's see, I made this. Okay, I have this UZI that goes from 0 to 255. I get the numbers. So first of all, the numbers goes into this subpatch. It's called int to binary, and this is a patch I found actually a method I found on the forum some time ago, and it's really clever because we get a list of 8 possible bits based on the number we input, and this is exactly what we want because we need a rule made of 8 numbers. So for every possible number we get a list formed of 8 bits. Even if the number is smaller, it does not cover 8 bits, we get also a list of 8 numbers. So let's see how it works. So the E operator is a bitwise operator, and it sees the intersection of 2 numbers. Let's actually see how it works. Let's display the binary with those numbers boxes. So let's say that I want to see where all the common ones in those 2 binary numbers. So if we have the true binary, the representation of the number 2 in binary, this is going to see where we have ones in common. So we have 1, but we have 0 here, so there's nothing in common, nothing 1 in common. But if we get 1 0 1 0, yes, we have a 1 in common, so it outputs 1 0 and a 1. Then let's see, 1 also 1 and 0 makes 0, 1 and 1 makes 1. Here 0 and 0, 0 and 1 makes 0, 0 0 makes 0. This first one is not in the operation because it's too far left. So it goes on like this. Okay, so this is used to actually filter numbers, to divide numbers in powers of 2. So we can have, let's see, in this case, when we have 2, this is that the bits that there's a 1. So it outputs a 1, but then we have this bit shift operator, which shift bits to the right of a number that we decide. So if we decide to shift bits of just one place to the right, he will do exactly this. So we get this 0 is shifted to the right and it disappears. So we have just 1 and so on. This 0 is shifted to the right on one place. If you want to shift it 2 places, we get just 1 and so on and so forth. Okay. So the id operator actually filters out the numbers for how I see it, and the shift operator shifts the bits, giving us only the leftmost bit. Alright? Because for example, when we have 128, it shifts 7 bits to the left, so we just have the leftmost bit left. Okay. So then we have to scale this list by 225 because we are working with sharp values and we want our matrix to have numbers for the 0 for the black and 255 for the white. So we use the WASP object to scale this list. And then we have to reverse this list because otherwise it wouldn't work. I'll explain you later. And then we join this list with the outcome of the ASCII, which is our index. This is our index. And this is our values. So we are using this to set the cells inside this matrix called rule sets, which contains every possible rule in an 8-bit number. So we fill this matrix called rule sets, and then when we want a rule, we're going to use this number box to get the cell, slice. We will just get. We will get a list containing the cell and the values, but we just want the values. So we are going to slice it, cutting off the first 3 values, just remaining with the last 8. And we are going to fill this matrix called the current rule with the object jit.fill. That so takes one cell of this matrix, which is auto planes, so for the 8 bits, and then we fill this matrix with the content of this cell. I hope it's clear enough. Okay, so for example, yeah. Okay, let's go now there into the init part of the patch, where we initialize the first generation with a white cell on the middle of the matrix. This is really easy. It's just we select the middle of the row, which is the X sides chosen here when you first choose the sides of your render matrix, your server automata. So we just get the middle of this row, and when this ASCII gets to the middle, it bangs 255 value, so a white value, otherwise it just bangs 0. And then we set the cells of this matrix, and yes, we get our first generation. Then let's see this cell getter subpatch, where we go to an index of 1 to x sides minus 2 because we don't want to deal with the edge cells. Yes, we just want to stay one cell away from the edges. So we go from 1 to x sides minus 2, which are this cell 1 and this cell here. And then we see we get these cells, the neighborhood, because we get the current cell, the cell which is on the right, and the cell which is on the left, and then we bang out the matrix. So we get those cells that goes here into the get rule index subpatch, and this is getting the values of every single cell, see if they are equal to 255 and outputs on 1 if they are, or at 0 if they aren't. We form the neighborhood here, which is a list of 3 numbers. Then we unpack them and we multiply the rightmost bit by 1. So we just get 2 or 0. No, sorry, we just get 1 or 0 because this is how binary digit works. You just have 2 to the power of 0, then you have 2 to the power of 1, then 2 to the power of 3. And yes, we unpack those, we see what numbers did we have, and we form we actually convert it from binary to integer with this operation by summing all the digits, and then we use this as an index to get our rule. Let's go there. Yeah, we use this as an index to get our rule. So well, for example, yes, we have 0, 0, 0 here, and then we use it like an index. We get 0, and so we get the first row of the rule, the first cell of the rule. Sorry, and we get 0. So it's just an index inside the rules, and it gives us our outcome value. Okay. Then once we get the actual rule, we use it to set this new value into the render matrix, which is actually a 2-dimensional matrix. We use the x index, which is this one, with epsilon sides minus 1, so we always update the bottom row, because we just want to update this, and then we go up 1 row later. So we use the set cell message to set the actual value into this render matrix, and yeah, after that, when the row is ended, we select the end of the row and bang out this matrix, which goes first to the render. We see that I reversed the values, so we have actually black values when the cells are filled, and white when they are empty. So this goes to the render. This goes to the next gen subpatch, which is just a submatrix that just selects the bottom row, and then update our cells matrix, which is this one. So this one is this one. And then last thing, it will offset our matrix on one position in the epsilon dimension. So the next generation is going to be always at the bottom, and the previous one is going to go up one cell. Okay. Then let's see the render sub patch, where we are just rendering this video here. A nice thing is the grid they made, which is it's made like this. You have the tick width epsilon parameter, which is tick width x parameter, which is the 1 divided by the number of rows we have, and the number of columns we have, and then the tick width epsilon, which is the number of rows, is 1 divided by the number of rows. But then we get the normalized coordinates. We set a grid color, and then we say if the modulus of the epsilon coordinates and the width of the epsilon width of the cell is less than a small number, we get the grid color. We do the same for the epsilon coordinates. If the epsilon in the modulus is really near to the end of the cell, then we choose the grid color. Otherwise, we just output the incoming matrix color, which is our cells, and we have a switch to switch this on and off. And I guess this is everything I had to explain. I know it has not really been really clear, but I hope it was somehow useful. So thank you for watching this, and see you on the next tutorial, which will probably be a more proper tutorial. But thank you again, guys. See you.